Hello everyone. In this video I'm going to talk about a very important operation in image processing, convolution, and application of that for creating linear filters and applying these linear filters to images. So a 2D convolution for images is defined as if your signal, your image is X, so it has so many rows and so many columns, and if your filter, or you might also call it a kernel, right? If that is this H that you can see, then the 2D convolution between X and H is defined as the summation goes from negative infinity to infinity of h at m and n, x at I minus m, and j minus n. Now, in general, the summations will never go forever because you only have what? A limited number of pixels, right? So this m and n, as I said, they are only going over the range of the kernel size. So they are not really like this. Or at least the infinity part of it you can cross out and just say summation over m and summation over n. Now, you might say, well, how do I perform this, right? And I here tell you the simplest and the best way to perform this convolution instead of expanding it. If you want to perform, let's say this is your image, this is your signal X, and this is your kernel H or filter H. If you want to do it is, or in this case actually it's going to be the other way around. Your H is the first one, your X is the second one. So the meaning of this I minus M and J minus N is to flip the signal. So and you see this negative is behind both of them. So in both X and Y direction, or horizontal and vertical direction, you have to flip the signal. So here, if this is X, the first thing I do, I flip the left and right. So the signal becomes 1, 4, and 2, 3, 5, and 1, and 1, and 0, and 2. Then I flip it upside down, and that becomes 2, 1, 2, 5, 4, 5, 0, and then 1, 3, 1. Okay, so now that you got this one, you are going to put this filter at each and every one of the pixels in H, center it with the location of interest, and do a pixel-wise multiplication. So for example, you can put that center 5 right here at what? At 13. So this is what's going to happen. The 5 is going to be on the top of 13. The 1 is going to be on the top of 7. 3 goes on the top of 19. 2, 0, 1 will go on the top of 14, 20, 21. And then on here, 2, 4, and 1 will go on 5, 6, and 12. And now you do what? You do basically multiplication element by element, or pixel by pixel. So you multiply all of these numbers together. And then add the result. And whatever result you get, that is going to be for this location. Right? And then you move this filter. So you bring that filter 2, 4, 1 and the other numbers, and you move it. You center it first here, then you center it here, here, go over each and every one of the pixels, repeat this operation, And what? We say it's a moving filter. You move it over each and every one of the pixels, center it at that pixel, do the element-wise multiplication, add the results, and replace the current value at the center with the result of that basically dot product. Correct? So for example, if I want to show you what's going to happen in the first pixel, then I have to bring this number 5 and center it right at the top left corner of the image. Right? Now, if I want to use the weights, so this 17 is multiplied by 5, correct? And then 24 is multiplied by 0. This 5 is multiplied by 1, 23 multiplied by 3. Then you might say, what about the rest of it? What about this 2 that you have? What about this 1 that you have? And what about the first column, which are basically 2, 4, and 1? What about these guys? These 6 of or 5 of the 9 entries of the kernel, they fall outside the image boundaries because this pixel was on the edge. What would you do? So here what we do is called image padding. We pad the image outside the image with layers of 0. So here, if I add 1 layer of 0 all around the image, right above, below, to the left, to the right, okay, of any pixel, I will add a 0 as well as the corners. So now when I want to do it, literally these entries of the kernel outside the image, they have no effect, they have no contribution. So the result is going to be 17 times 5, which is 85, that's 0, plus 5, that's 90. 90 plus this is 69 should be what? The result of this whole thing should be 159. Now, is that really that number? Yes. So let me show you. I have written a code in MATLAB. So this is that A, this is H or X and H, whatever you want to call it. And here I use the command conv2, which is used for 2D convolution, and I pass to it the first signal and the second signal, or the image and the mask, really in general. And when you pass to it, you have the option to say same or not say it. If you say the same, what does it mean? It means the result of the convolution is going to be the same as the original signal. If you don't say it, then the result of this filtered signal or convolved signal will be larger than both of them. Okay, so I show you both versions here, and this is the version that we didn't use the keyword same. Here is the version that we did. Remember, my A is 5 by 5, so here you see the filtered version. Convolved version is also 5 by 5. And if you look at the top left corner, you see the number is what? 159. So it does absolutely make sense. Okay. And you can move that filter now to any other location in the image. Center the center of the filter with the pixel of interest. Multiply all of the entries of the kernel with the entries covered in the image by the kernel, and add all of those numbers together, and that number, whatever you get, should replace the pixel of interest. So now this number is going to sit here. I'll do it for one more pixel. Let's say, for example, for this 21. What should I do? What should I replace the row 4 and column 4, which is 21, in the filtered version? What's going to be? So again, I use the same weights that you can see here, right, which are 2, 1, and 2. And then you have 4, 5, 0. And then you have 1, 3, and 1. So if I do that, right, you have a 44, you have a 9, which is 53. That's 73. That's 79, 79 and 105 that you have here. And then you have a 26, a 25, which is 51. And then here you have a 76 again, right? And I bet we can easily add all these numbers together, right? That's 130. And this is 181, correct? So 181 plus what? 130, which is 313. If I did the math right, let's go back and look at it. Here we go, 311. Okay, seems like I need to work on my math, but yeah, 311. I don't know where I got this 311. It's 181 plus 30. 311, and this is 311. Okay, so clearly you see that I did it right. So you just slide, as I said, you just slide the filter right to each and every one of the pixels, center it, and each and every one of the pixels, do the dot product, add the result, replace the pixel with the result. And this is the convolution. Now, a few questions. One is, should I always add one layer of zeros to the outside the edges of the signal? The answer is no. So how many layers of zeros should I add? Well, that depends on the size of this filter. Here my filter was 3 by 3, so I only needed one layer. Where did I get one from? So this 3 is subtracted 1 from it and divided by 2, and the result is 1. If you get 1, then you need one layer of zeros. If, let's say, your filter here, this guy, was instead 7 by 7, how many layers of 0 you need for padding? It's going to be 7 minus 1 divided by 2, which is what? 3 layers of 0. So now you have to add 3 layers of 0 next to each edge pixel, and so on. Okay, so this is about how many layers of 0 you need. And a few other things is, one, as you clearly can see, your filters are always n by n, so your filters are square filters. The other thing is your filters, the size of the filters are odd numbers. So you do not use a 4 by 4 filter. You always use a 3 by 3, 5 by 5, 7 by 7. So the size of filters are odd and they are always square. That's another point that you have to consider about the filters. And the other question you might ask is, what was that case that it wasn't the same size? How big is that? So if you look at the size of this guy, it is 7 by 7. And if you look at the central part of it, which is basically from here to here, and then from this 98 above all the way to 169, that's exactly this guy. So if you look at the central part of this 7 by 7, which is a 5 by 5, that is exactly what? This guy that we have with the same size. So what are all of those extra ones here? Like, for example, what is 17? And why is it that the size of this version of convolved is not 5 by 5, it's 7 by 7. Where do you get 7 by 7 from? Okay, so where does this come from? How do you determine the size of it? Let me answer the second question first. So in general, if you don't apply that same option that I showed you, How do you get it? If your signal is n by n, and if your filter is m by m in general, okay, the result of this convolution is going to be what? N plus m minus 1 by n plus m minus 1. This is the result of convolution without the same option. So in this case, n is 5, m is 3, so you will get 7 by 7. Okay, so that's the answer to your second question. Now, what's the answer to the first question, right? Remember here, when I did this, if you look, this corner here, if you look, I have a 17, and then 75, 90, 35, 40, right? 17, 75, 90. Let me go back here. This 17 kind of look like the same 17, but what is it really? So let's talk about it. So where do we get those extra numbers? Well, if you want to do convolution, you have to do it for placing basically this filter all over the image, even if there is only 1 pixel overlap between your filter and your image. In the previous case, when I calculated this number, if you remember, 4 of these numbers were used to calculate that number, which was 159. 4 of the numbers were used. So out of the 9 numbers in my filter, right, 4 of the numbers that I'm putting in circle were used to calculate 159. But that's not the minimal overlap that you can have between the 3 by 3 filter and this image 5 by 5. If you want to get what? Minimal contact, then your minimal contact would be like this. 8 out of the 9 numbers will not have any contact. Only the bottom right side of the filter will have an overlap with the top left corner of the image. And what is this number? If you look at it, that's 1. So the only thing you will get is a 17 by 1. All of these outside will be multiplied by a 0. So the result is simply 17 times 1, which you can see over here, 17. Now you might say, what about 75? Let me show you that as well. So for 75, I slide this filter 1 unit to the right. So now it is going to have 2 entries contact. So now you have these 2 contact, and the rest of it will be no contact, no overlap. And what are these numbers? Well, if you look, when it comes forward, these 2 numbers will be in contact, 3 and 1. So what would you get? 3 times 17, which is 51, plus 24, which makes it what? 75, and that's what you see here. Okay, so in general, as I said, n by n, m by m makes it n plus m minus 1. That's the size. Now, when you say the same, it only picks the central part of it, which is the same size as your original signal. Because it was a 5 by 5, it picks the middle 5 by 5 part of it. So that's what the operator same does. So hopefully now you know how to perform a 2D convolution in an image. Now you might come and ask me the good question. Okay, fine. I know how to convolve an image by a filter or by another signal. Now what's the point? Where would you use this convolution in real life? And I say that's in image filtering. Some of these convolutions by some specific filters or kernels, they create some interesting effects in an image. You might say, like what? I would say, for example, if the kernel you convolve with is basically let's say a 3 by 3, 5 by 5, 7 by 7, where this number in each and every one of the entries is equal. So if it's 3 by 3, then it's 1/9 all over the place. If it's a 5 by 5, correct, then what? Then since you have 25 cells, each one of these cells is going to be 1/25. Okay, in other words, sum of all the entries, when you add sum of all of these numbers together, it will give you a 1. This filter is what we call an averaging filter. Why? Because when you put it on any region of the original image, what it does, let's say you put it right here, correct, this 3 by 3. At the center, which is here, the new value is going to be the average of all surrounding value, because that's exactly what this one is. It's 1/9 at the center plus 1/9 of all adjacent pixels. So it replaces each pixel by the average of not only that pixel, but all other 8 neighbors. So it makes it the average of 9 pixels. And this is called averaging. And what's the effect of averaging? Well, it's blurring the image or smoothing the image. Now, blurring in general is not something that you want to do in an image unless your image has noise. If your image has noise, then blurring the image will cancel to a good part the effect of noise. We call it denoising or noise filtering. And one of the simplest way you can achieve it is using an average filter. But is the average filter the only filter that can do the blurring or smoothing? No. There is one that is a little bit better, and that is called the Gaussian filter. What is a Gaussian filter? Well, as the name says, it is coming from the Gaussian function, or the normal function, but 2D version of it. So instead of just a single number, negative of a single number like x squared over 2 sigma squared, now it's negative of u squared plus v squared, where u and v are the pixel coordinates. Okay, so this is the 2D Gaussian function. And for different sizes of the kernel and for different choices of sigma, the numbers that you see will be different. So for example, if you choose the size of the filter to be 3 by 3, then for a specific sigma, what it looks like, if I can zoom in, is going to be like a peak. So you know the Gaussian function is like this, correct? In 2D. Well, in 3D, it is what? It is a similar thing, but it is like a rotated version of that, correct? It is basically a peak like this, correct? So at the center, you have a big value. As you get away from the center, you get smaller numbers. And that's exactly what this one is. Unlike the average filter, where the weight of all of the surrounding pixel and the pixel itself, they are all the same. They contribute the same amount to the new value of the pixel. In this case, that's different. The center location contributes the most because it has the largest number. And as you get away from that, the numbers will drop. Okay, so here the numbers in red, they are quite smaller than this number in blue because that's the center of the Gaussian. And if you look at these coefficients for a 3 by 3 with a specific sigma, you see that, for example, these guys are like 1/16 each on the diagonal, which are a little bit further away. The direct pixels on the left, right, above, and below are like 1/8. And this signal at the center is 1/4. Okay, so the center signal, it definitely contributes more. And one other important thing that you might notice here is, if You remember I told you if I add all of these numbers together, the result is what? 1, right? That's the same thing here. Look, if you add all of the numbers here in this Gaussian filter again, you add all of these numbers together, again, the result is 1. And you might wonder, why should that be the case? Is that always the case that I choose these coefficients such that sum of them is always 1? Well, not always, but for many operations that is the case, especially if you are to replace the original image. And the output is another image, not something like we'll see later, like an edge. Okay, if the result is to have comparable quality with the original image, so it is another image really, then we want this summation to be 1. Why? Because if it's more than 1, then it is going to make all of the pixels in general brighter. And if you have already some bright areas, it makes them very bright, so it makes a saturation effect, right? And in general, it changes the light intensities, shifts the border and everything, okay? So we want still the sum of the numbers to be the same as sum of the original numbers on the filtered and unfiltered image. So the borders of the image, the edges and so on, they are not dilated or shrunken or anything for that matter. And one thing difference between the weighted average and the Gaussian is the smoothness. If you look here on the right, you have Gaussian, on the left you have the average. Clearly you see the Gaussian does a lot better job compared to the average. In average, you clearly see pixelations, right? You see some kind of rough edges, while here you see a lot smoother edges. Okay, so in general, if you want to smoothen an image or reduce noise or something, I absolutely recommend you choose the Gaussian filter instead of what? Instead of the average filter. And let me show you the effect of that on the sample code that I wrote here. So how do you create these filters? Well, you can either define them like a matrix by just typing the numbers, or in MATLAB there is this built-in function called fSpecial. With fSpecial, you just pass to it the name of the filter and the parameters needed for the filter, and it creates that filter for you, which is really great. So you say, give me an average filter with the size 9. So it's 9 by 9. And so the weight of each and every one of the entries is going to be 1 over 9 squared, which is 1 over 81 really. Or you say, make it a Gaussian with a size 9 by 9, but sigma is 3. And you might say, what's the effect of the sigma? Well, the effect is how fast this peak that I mentioned to you, correct? This peak, how fast it is going to shrink to 0, or it is going to be, of course, what? Wide like this. So this is a bigger sigma, this is a smaller sigma. Okay, so here I chose a sigma of 3 units, and typically remember that for a Gaussian distribution, how far is this kind of maximum meaningful, or 99% of the data or so? It is 3 to 4 sigma, okay? At most 4 sigma, typically 3.1 or 3.2 sigmas. So if I want to say how much is this roughly, it is about 3 sigma. You can go to 4 sigma, but then the numbers at the tails are going to be so small. So plus or minus 3 sigma from the center. And when we don't specify the center for this fSpecial, which it doesn't have the option for it, the center is at 0. So mu is at 0. So it is really 3 pixels if sigma is 1, let's say. 3 pixels to the left, 3 pixels to the right of the center have a meaningful non-zero Numbers anywhere after that, you get what? You get almost close to a 0. So when I say what? When I say my size is 9 and sigma is 3, I'm sure that 3 times sigma on the left, 3 times sigma on the right is about 18, while the size of the kernel is 9. So nowhere around my kernel I should have black areas. Of course, they're going to be darker than the center, but nowhere it's going to be almost 0. So for me, this kernel will basically spread well all over the entire size of it. And here I have filtered using the conv command my image with the edge average and edge Gaussian. I use the same operation, and here I'm going to show you the result of that. So here we go. Run this one, and run this guy. And these are the results. So this is the original image. And clearly, if you look, let me just zoom into a specific area, you should be able to see the blur, right? You clearly can see in the face now, right? And let me do it here too. So the blur is completely visible in the two smoothened version versus the original one. And if you compare here, let's see if I can zoom in a little bit more. Maybe you can see it, maybe not. You need to probably see the two images in big size, not here like a subplot. If you put them side by side, you should be able to see that the Gaussian does a little bit better job than the average filter in terms of the smoothness, okay? Also, I mentioned using this Gaussian or average filtering to get rid of noise or make it better. Here I have added some salt and pepper noise using the command imNoise to the image with some intensity. And I show you that if you apply this smoothness, you can get rid of that noise. Of course, you lose some details, but they're going to be much more tolerable compared to the case that you have salt and pepper noise on it. So here, let's take a look. So this is the original image with noise, salt and pepper. And you see here, when I applied the average or the Gaussian, in both cases, the noise is gone. Okay, because those single pixels that are black or white, salt and pepper, are now going to be replaced by not only themselves, but by the contribution from all of their surrounding pixels. And since the surrounding pixels are not corrupted by noise, they will dominate the center pixel, and they will make the final result better. Now, clearly, in general, for that kind of noise, the average might be better than the Gaussian, because the average will, in the average filter, the surrounding pixels that are not corrupted, they contribute equally to the center one that is corrupted, compared to the Gaussian, where the big guy is the center pixel, and the contribution of the surrounding is not going to cancel as much as the noise at the center compared to the average one. So each one of them might have their own application depending on the type of the noise that exists, right? If it's a Gaussian noise, this one might help better. If it's a salt and pepper, the average one might help better. And but in general, you see both of them can eliminate the effect of noise to a good extent. So this is the smoothening of image and getting rid of noise. Let me also add here denoising, right? And this is one major application of these filters. One of the other important things for which I'm gonna have a separate video soon is edge detectors, right? Edges are where the light intensity has a sudden increase or a sudden decrease. And the edges are not all like this step behavior. Some edges are like this, or most of the time they are like this. Okay, so not every single edge is a step. Sometimes they are like a pulse, rectangular pulse, trapezoid pulse, or something like that. But the important thing is to calculate what? A sudden increase or a sudden decrease at the rising or the falling edge. And there are so many filters that can give you such thing. The simplest one is called the Prewitt filter, which is basically they are like, if you use the centers to be all zero, let's say if you use a 3x3 filter, if you don't do anything at the location you are, but anywhere to the top of that you multiply by a 1, anywhere below that you multiply by a -1, here you can detect the change in this direction, which is basically a what? A horizontal edge. Okay, so if you have a horizontal edge in the image, this filter will detect it. On the other hand, if your filter is like that, on the left you multiply by 1, in the middle nothing, on the right you multiply by -1, this measures, it shows a big response where you have a vertical edge and you're passing through it and nowhere else. So this is a vertical edge detector, this is a horizontal edge detector, and you can see them here. You can see here, this is like your vertical one that is applied to the original Einstein image, and here is the horizontal one. If you can see here, the horizontal edges are more dominant and basically demonstrated themselves, right? You can probably see them much better in the eye area or in the hand area, while here the vertical edges, you can see them here, right, or here, that the vertical edges are much better detected. Okay, so in this case, for the edge detectors, sum of all entries in the kernel is not equal to 1, it is equal to 0, because the result is not a replacement for the original image, it's just detecting some details of the original image. It's the edge map of the original image. So for edge detectors, the kernel does not need to be summation of it equal to 1. Actually, it is equal to 0. Okay, for edge detectors, sum of the entries equal to 0. And Prewitt can give you horizontal or vertical edges. There is another one which is called the Laplacian operator. In Laplacian operator, you basically are doing a second derivative. Because if you look at the Prewitt is like a finite difference formula, right? So this one is like what? This is like the derivative of the light intensity, or the partial of the light intensity with respect to the y direction, and this one is like the partial of light intensity with respect to the x direction, correct? How would you do that? You do the derivatives numerically using finite difference. So you say, for example, this partial of I with respect to y is what? You say this is the I at y plus delta y. This is minus I at y minus delta y, and then divided by 2, right? The center finite difference formula. And this is exactly what you're doing, right? You are taking it at the next y minus the previous y, or the other way around, the previous y minus the next y. This middle pixel has no effect, and whether you multiply it by 1/2 or not, that just changes the intensity of them. But clearly this is the central finite difference formula, right? And this one is partial with respect to x. Now the Laplacian is basically a second derivative, and this is like second derivative of I with respect to x squared, plus second derivative of I with respect to the y squared. This is the Laplacian operator, del squared of I. And if you use the center for a finite difference formula, the simplest thing to do is at the center you have a -4. All surrounding, above, below, left, and right are going to be 1, and diagonals are going to be 0. Okay? And the good thing with Laplacian is it detects all different directions. If you look here in the Einstein image, you clearly can see that all different directions are detected. Okay, and it does it by looking at the second derivative, right? Whether the second derivative is like the second derivative test for a maximum or a minimum or a sudden change instead of the first derivative. And it detects a bunch of different directions, specifically x and y for sure, all of them. So this is another edge detector. Now it's not going to be as pronounced as the Privet, but you can basically reinforce it by multiplying them by some gains. But again, if you look at some of all these numbers, you clearly see some of them equal 0. There is another one which is called Laplacian of Gaussian, which is basically what? You first apply a Gaussian filter to the image to smoothen it, then you take the Laplacian of the result. Okay, so it's Laplacian of Gaussian, and so you apply this these two second derivatives to this Gaussian function, and the formula for the filter is like this. And you might want to say, okay, what's the purpose? Why do you apply Laplacian and Gaussian? Because Gaussian does blur, Laplacian does detect the edges. So what is it? And you're right. The goal of it is to detect the edge in an image where the light intensities on the two sides of the edge are what? Noisy. So if you want to detect edge detection in a noisy image, which many times the images are not that clean and nice, that the edges look like these straight lines like this. They might be noisy. So first I apply a Gaussian to it. Gaussian makes it smooth like that. Now I apply a Laplacian to it. And Laplacian is going to give me a big response at the edge. Okay, so Laplacian of Gaussian is an edge detector when you have noise in the image. And let me show you the result of these different edge detectors as a convolution, not using the command edge, because in MATLAB you have the command edge, but here I want to show you that if you read the image and apply it. Now I can use a noisy image or I can use the original image. For now, let me just use the original image, Lena, instead of the noisy version of it. Okay, and let me show you what happens. So here again I use the command F special, but instead of passing average or Gaussian to it, this time I say give me a Laplacian. And here I provide a factor called alpha. This alpha determines the shape of this Laplacian, because Laplacian is not always just like what you see here, right? There are other shapes of Laplacian too, controlled by this parameter alpha. When you say alpha is 0, it's exactly this guy that you see here in the image. 1, 1, 1, -4 at the center, everywhere else is 0. Just look into the help of MATLAB for F special and Laplacian. LOG, as I said, is Laplacian of Gaussian. You have the kernel size and you have the sigma for the Gaussian, and you have the Privet. So here I do the convolution with the same option and I run it. Let's take a look. So this is the image Lena. This is the LOG. It detected the edges of the image for me. You see the Laplacian did detect the edges, but clearly the LOG is doing a lot better job than this one. Why? Because my original image is not super clean. There is noise to it. So when I directly take second derivative, the result is not so clean. I'm taking derivative of the noise, and you know that's not something you should be doing. That's not the best action to take what? Derivative of the noise. But look here, when I first smoothened the image, then I took the derivative. My edges are much cleaner in LOG compared to just the Laplacian. And here is the privet, right? And the privet can do a relatively decent job too, but clearly you see, because the image has noise, originally the LOG did quite better than the rest of them. Okay, so this is for edge detector. The last topic I want to talk about is the sharpening. And sharpening is basically first detecting the details, the edges, by subtracting the image from the smoothened version of it. So if you subtract the image from the smoothened version of it, the result are really the details that the smoothened operator has eliminated, correct? When you do smoothing, you are throwing away these kind of details, sharp details. Now, if instead of me throwing these details away, that I did by applying a smoothing filter, I go ahead and add those details to the original image. So basically what? Reinforcing those details in the image, because those details already exist in the image. Now I'm adding a fraction of those details again to the image. So if the intensity here at a detailed location was I, now the total result is going to be I times 1 plus A, where A, as I said, is a fraction less than 1 that you want to add to the details. So let's say if this A is 0.2, now you are making the details 20% stronger, right? So you take the details and add a fraction of them to the original. This is a simple operation for sharpening. And a simple kernel that can do such job is this kernel here. Again, if you look, sum of all of the entries is 0. Because again, I'm not gonna really work with the original image and replacing it. I'm just adding some extra details to the image, and because of that, this summation is equal to 0. And here I have done this for you. I am reading the image Lena, and I'm using 20% fraction of details to add to it. You see here, I first applied the Gaussian. I subtracted the Gaussian from the original to get the detailed image, and then I added the detailed image to the original. Now what I did here, I did not exactly do this formula. I multiplied the original image by 1 minus A. So basically what I did was alpha blending. Alpha for one of them is 0.2, for the other one is 0.8. Why did I do that? Because I did not want the resulting image to have expanded white areas. Okay, so you can do that if you want. You can get rid of this 1 minus A. Okay, let me show it to you. So one time I can do this way and show the result to you. So here is the image. Here is the detail that I eliminated in the Gaussian operation. And here is the sharpened image. As you look here, this image definitely looks a little bit sharper than that. But if I put back that 0.8 and redo it, I believe this one looks a little bit better. Okay, it's not kind of whitened a lot. And again, if you really want to see the sharpness of the bottom image compared to the top image, it is a good idea that you see them in large size. So let me show you in large size, side by side. Maybe that one can do a better job on showing you that it's really sharpened. So here, this is the original and this is the sharpened version. Let's see. You can see some big difference. The way I see it, maybe not too much, so let me get this guy back. And I'll do it one more time for you. Just trying to see if I zoom in, because from where I'm sitting and looking at it, the sharpness is a little bit clear, but in the video I'm not sure whether you can see that sharpness very well. So here again, let me zoom into one area and show you really that there is a little bit of sharpness. Maybe in the hair, that's the best area to see high frequencies. So if I zoom into this area versus here, the very same area, if I can zoom in, if you look here in the center and here, it is clear that the white edges are a little bit brighter, not too much because this A is not a big number. I can bump it up clearly if I want to and recalculate everything. Okay, let me close all of this, redo it one more time, and then hopefully you're able to see something meaningful. So now this is the original, this is the sharpened, and again I can clearly see this image on the right is a little bit sharpened, but let me just zoom into one area before I finish up the video and see, hopefully I can show you a good snapshot here. Yeah, I guess now you can see it quite better. If you look at the light intensities here, they are on the edges, they are quite brighter compared to here on the left, and that means this guy is basically sharpened. Sharpened means the small details are more pronounced compared to the original image. Okay, so hopefully I could convey to you the notion of convolution, how to do it, and where would you use convolution in image processing. So thank you so much. I will see you in my next video.